Hello everyone. In this session, we will be discussing about some of the basic concepts of Zener Diode. This is its symbol and this is its image. This symbol indicates that the current flows in both directions. So, first of all, a Zener Diode is a heavily doped semiconductor device that is designed to operate in the reverse direction. When you speak about a Zener diode, it operates just like a normal diode when it is in the forward biased condition. But when the voltage across the terminals of a Zener diode is reversed and the potential reaches Zener voltage, that is the new voltage, the junction breaks down and the current flows in the reverse direction as shown in this particular figure. This effect is known as Zener effect. Okay, if we see here, when connected in the reverse biased mode, initially a very small amount of leakage current flows through the diode. As the reverse voltage increases to the predetermined breakdown voltage, that is Vz, current starts flowing through the diode. Okay, and the current increases to a maximum which is determined by this particular series resistor. We have already discussed about Zener effect or Zener breakdown. Okay, when you speak about Zener diode, there are two different types of breakdown. One is known as Avalanche breakdown and the other one is Zener breakdown. So first, let us learn what exactly does Avalanche breakdown mean. This particular Avalanche breakdown occurs both in normal diode and also in Zener diode. Because the junction is reverse biased, the depletion region widens, because of which the number of immobile ions also increase, thus leading to a stronger electric field. Okay, and this in turn accelerates the minority charge carriers in the vicinity of the depletion region. When a high value of reverse voltage is applied to the PN junction, the free electrons gain sufficient energy and accelerate at high velocities. These free electrons moving at high velocity collides other atoms and knocks off more electrons. Due to this continuous collision, a large number of free electrons are generated. As a result, current in the diode rapidly increases. Let us learn this in detail. So now let us see how exactly this breakdown occurs due to the collision part. Okay, now consider this to be the free electron which has gained enough energy, and these are the immobile atoms. So what will happen now is that this particular electron, okay, it has sufficient energy that it collides with some atom. Okay, then what happens, this particular electron or free electron will knock off some more free electron from this particular atom. That is, this will generate another electron over here. Okay, now we have two free electrons in this particular system. So what happens is these two electrons, okay, will collide, okay, with some more atoms. Fine, and then what happens is we have totally 1 2 3 4 free electrons here. Okay, then this collides over here, this over here, this here, and this here. Totally, if we see, let me just change the color to give it a clear view. Now so 1 2 3 4 5 6 7 8. This already generated 8 electrons in the system. This continues in the same fashion, generating abundant amount of free electrons in the system. This sudden increase in electric current may permanently destroy the normal diode. However, a Zener diode is designed to operate under the avalanche breakdown and can sustain the sudden spike of current. Let's consider the next topic. So this is actually achieved earlier than avalanche breakdown because of heavy doping. So now we will learn how exactly Zener breakdown occurs. First thing we should know is, as already specified, Zener diode is heavily doped. Okay, so it is represented in this format, P plus and N plus. So fine, because doping is so heavy, what happens is the depletion region is very narrow. Okay, so now we have applied reverse bias. Then what happens is, first point here, the depletion region is narrow, so a lot of immobile ions are present in this narrow depletion region. That itself generates a strong electric field. Upon that, we are increasing, as we increase the reverse bias voltage, the total electric field increases. Okay, now initially what happens is, the minority carriers which are present here, okay, they try to cross the junction, but at one point of time the electric field generated will be so strong that it will knock off or it will pull the electrons from the covalent bond. So covalent bond breaks and the electrons are like pulled towards the other side of the junction. Fine. So at one point of time, this particular current reaches to a very high value, and that is Zener breakdown. Next we'll come to the VI characteristics of a Zener diode. As we can see here, it's divided into two parts, that is forward characteristics and reverse characteristics. Okay, so in forward characteristics of Zener diode, the first quadrant in the graph represents this particular characteristic. And from the graph, we understand that it is almost identical to the forward characteristics of any other PN junction diode. Okay, but what is important in Zener diode IV characteristic is its reverse characteristic. Because as we can see here, forward bias region or forward characteristic is almost similar to, or almost you can say identical to the forward characteristics of any other PN junction diode. Okay, so coming to the reverse characteristics part, when a reverse voltage is applied to a Zener voltage, initially a small reverse saturation current flows across the diode. This current is due to thermally generated minority carriers. As the reverse voltage is increased, at certain value of reverse voltage, the reverse current increases drastically and sharply. This is an indication that the breakdown has occurred. We call this voltage, breakdown voltage or Zener voltage, and it is denoted by capital V and small z. Okay, Vz. Okay, and one thing we should notice, usually at around 5 volt or below 5 volt, we have Zener breakdown occurring, that is below 5 volt, and above 5 volt it is avalanche breakdown, and at 5 sometimes both avalanche and Zener, both breakdown occurs simultaneously. Okay, so next thing that we should consider is Zener diode specifications. These are the common terminologies which are used when we speak about Zener diode. First one is Zener or breakdown voltage. Okay, it could be called as Zener also or breakdown voltage also of Zener diode. The Zener or reverse breakdown voltage ranges from 2.4 volt to 200 volt. Sometimes it can go up to 1000 volt, while the maximum for the surface mounted device is 47 volt. When you speak about current, that is the maximum current Iz. It is the maximum current at the rated Zener voltage, and its value can range between 200 microamps to 200 amps. Okay. Next we have current Iz minimum. It is the minimum value of current which is required for the diode to break down. Fine. Next what we have is the concept of power rating. It denotes the maximum power the Zener diode can dissipate. It is given by the product of voltage of the diode and the current flowing through it. Okay. Then here we have temperature stability. Diodes around 5 volt have the best stability. Coming to the concept of voltage tolerance, it is typically plus or minus 5%. Zener resistance is the resistance that the Zener diode exhibits. Next, let us speak about Zener diode as a voltage regulator. Before this, there is one thing that we should speak about, the Zener diode, this particular graph. Okay, let us consider a Zener diode equivalent in reverse biased mode. So a Zener diode equivalent consists of a voltage source. We can consider its value to be Vz0 and a series resistance Rz as shown here. Now if we see this particular graph, when we extend the linear region line to x-axis, it cuts x-axis, and this point is the Vz0. Okay, and then we have another terminology called as Vzk, which is the knee voltage. Okay, and let us take some random point on the line. Let us name it as Vz. Then Vz is given by Vz0 plus Izrz. If in case we ignore or neglect Rz, then immediately Vz will be equal to Vz0, where Vz is the Zener voltage. Okay, so this is why when Zener diode is used in parallel with a load, it will offer a constant voltage of Vz. Okay, actually it is not that constant, because here we have the value Vz equal to Vz0 plus Izrz. Okay, there is some internal resistance offered by the Zener diode, so that will provide some slight variation, but if we ignore that internal resistance, then we can say that a constant output voltage of Vz0 is offered, or Vz is offered. Okay, and yeah, coming to the Zener diode as a voltage regulator, Zener diode is used as a shunt voltage regulator for regulating the voltage across small loads. The breakdown voltage of Zener diode will be constant for a wide range of current. Okay, Zener is connected parallel to the load to make it reverse bias, and once the Zener diode exceeds knee voltage, the voltage across the load will become constant. So other than this, the Zener diode is also used in overvoltage protection, clipping circuits. One thing that I didn't mark is VZK. It is the knee voltage after which breakdown occurs. That's all about today's session. Thank you.